So we're going to start up our new unit, and like our last one, we're going to deal with systems of equations. This time we're going to deal with specifically linear systems. So it'll be much easier, stuff that we started in Algebra 1A. We're just going to talk about infinite many solutions and get into a specific type of word problem involving a current, either wind or water. So our goals: know how to solve the linear system all three ways: graphing, substitution, elimination, and then how to apply it to a word problem. So solve by graphing, same concepts as in our last unit. What we're going to do is we are going to graph each equation, and then we will find the point of intersection. There are three cases that we can have. We can have them intersect once, be parallel lines and never intersect, or they can be what we call coinciding lines, and they'll intersect in infinite many places, but not all real numbers. It'll be every point on the line. Okay, so let's take a look at the first linear equation. We could go get y by itself, like we've done since Algebra 1, or we can use some of the things we learned in Algebra 2 or in College Algebra A, and what we learned at the very beginning of the year. The slope, we'd have to subtract the x term over, so we do the opposite of the a coefficient. Then we'd have to divide by 2. And then our y-intercept would be 0, 4.5. Now, whenever I get a decimal for my y-intercept, I'm immediately going to go find the x-intercept, because sometimes that's easier to work with. And that's what we're going to work with in this problem. You put 0 in for y, you're going to get what? X is 3. So let's go plot our point, 3, 0, and then use our slope, down 3 over 2. I can use my slope backwards, up 3 backwards 2, 3 backwards 2. We have a y-intercept at 4.5. And if you really wanted to, you could use the slope from this point as well and put a lot of points in there and get a nice line. You want to make sure that your first line is super accurate. And then your second line, you just do enough points so you can either see the point of intersection or enough so you can cross the line and then try to estimate the answer as best as you can. Sometimes in the homework, you're going to have to estimate so you can when you solve by graphing. So the slope here, we'd have to subtract the 2x over and then divide by 5, so it's negative 2/5. And our y-intercept would be 0, negative 1. Our x-intercept would be negative 2.5, 0. You don't have to find the x-intercept in this one since the y-intercept is really nice. But sometimes it's nice to have, just to see if your graph will actually cross that point like it's supposed to. So if I go up 2, backwards 5, then my y-intercept go down 2, right 5. And then as best as I can, draw my line. And then we look for the point of intersection, which is right here. And so our solution is the ordered pair 5, negative 3. All right. So the next thing we're going to do is we're going to solve a problem using what we call the substitution method. Same concepts we had before. You want to replace an equal thing with an equal thing. So you're going to get something equal in one equation, put in the other. Often with linear equations, we will isolate a variable. But sometimes you'll see that you have 2x in both equations. Then you can isolate the 2x. You don't have to get x by itself. Once you isolate a term that you can replace in the other equation, you will replace in the other equation, you solve, you back substitute, write your answer as an ordered solution to represent a point. So we're going to try to find an equation that we have where we can get a variable by itself. You just pick whatever you think is easiest. It really doesn't matter. So I'm going to take the second equation and isolate the x. So we add 7y and divide by 2. All right, so after that, what I'm going to do next is I'm going to take this expression right here and plug it in for x in the other equation. Now I go to the first equation, and now we have 3 times 7y over 2 plus 3 halves plus 5y equals 2. All right, so then we just take this and we solve this equation. So I can distribute the 3. Just multiply to the numerator. And there's 3 over 1, so we're not going to change our denominator. And if the fraction's really, really bugging you at this point in time, what we can do is we can just times every single term by the least common denominator, clear our fraction. Don't forget to multiply the other side. And then we'll collect our x's on one side and our constants on the other, or sorry, our variable on one side and our constant on the other, the y. And then we divide by 31. So we have the y coordinate, and now we have to find the x coordinate. That's where we go use what we did in our very first step, and we replace every y with -5/31. So when we go back to that second equation, I have x equals 7 halves times -5 over 31 plus 3 halves. And at this point in time, you can use a calculator or your 5th grade math and simplify this. Get a common denominator here. So I'm getting the x coordinate is 29 over 31, and the y coordinate is -5 over 31. So with this example, we're letting you know that we don't care if our answers are whole numbers or fractions. In college algebra, we don't discriminate. You should be able to handle any type of number we give you. All right. So the last method we have for solving linear equations is called the elimination method. What we want to do is we want to get the same number of different signs, or what we call opposites, in front of either the x or the y. It doesn't matter. And then we'll eliminate. And then we can either back substitute or we can eliminate again. So think about that last problem. The fractions were really, really nice. And I know a lot of people really just don't enjoy working with fractions. So what we could do is we could eliminate, get the ugly fraction, go eliminate the other variable, and the only thing we really would have to ever do with our fractions is reduce them. So let's take the exact same problem with that really ugly answer, and let's do the elimination method. So first thing I'm going to do is I'm going to go get rid of x. I'm going to times the first equation by 2. And times the second equation by -3. That way I can get opposites in front of my x. And then I end up with what? 31y equals -5. And just like the last time I did this problem, the y is still -5/31. So I know the second half of my ordered solution. Now what I can do is I can go get rid of the other variable. So this time I'm going to eliminate the y value. So I'm going to times the top equation by 7. And times the bottom equation by 5. They're already opposites, so I'm going to end up adding this time. And now I get 31x equals 29. So x is 29/31, just like the last time I did this problem. So that's just a quick review of the three methods we already know how to solve systems of equations. We did it last unit. We're doing it again. All right, so the next thing we want to do is we want to go classify our answers. So there's a couple different ways we can classify them. First type is, does it have a solution or not have a solution? So if something has a solution, we say it's consistent. If it doesn't have a solution, we say it's inconsistent. So whenever you hear the inconsistent, you're really thinking of no solution. If the equations are independent, then that means we have one solution or a finite number of solutions. It means the equations are going to have an answer that where the x value is not dependent on the y value. It's independent of what the y value is going to be. Independent is our one solution. We just try to answer it as an ordered solution. Okay. The last type is called a dependent solution. And this is when we think of, okay, we have infinite number of solutions that do not write all real numbers. If you write all real numbers in these problems, you're going to get 40% for the problem. You haven't told us what the answer was, okay? You just told us how many answers there are going to be. That'd be like me doing the first three examples saying there's one solution. That really doesn't get you much credit. Okay? There are two ways to write it. The first way is what you did in Algebra 2 and College Algebra A, where you write the set builder notation, where you write the equation and state. Because in two equations, two variables for a linear system, the equations will be multiples of each other. There is another way to write this system. It's called parametric form, where you write x is x, and then you go put y in terms of x, or you can say y is y, and you put the x in terms of y. So you're writing a formula for the ordered pairs. So that's the parametric form. This is the form we're going to have to get used to do some of the worksheet for 5.2, because we're going to give you 4 problems that use parametric form. Now, when you get to 3 equations, 3 variables, the set builder notation and the parametric form notation, they will be used for different types of infinite many solutions. But with a 2 equation, 2 variable, there's only one type. Now, the easiest thing we can do for equations, and we'll want to get used to this when we get to the matrices at the end of this unit, is you always want to simplify if you can. So you want to put things in what we call true standard form. So this first equation, I could divide everything by 3 and make it just a little bit easier to work with. So we'll just say we're taking 1/3 of every term. In the second equation, they're all even. So I could cut them all in half. So I got negative 3x minus 2y equals negative 6. Well, now I can start working with these. Instead of trying to find the least common multiple of 6 and 9, which is 18, a lot of people try to do 54 and do too much work. I can reduce them down. It's a whole lot easier. In fact, when I look at these, I already have opposites for the x, so let me go just add them right now. So I get 0, and the y's add up to be 0. Be careful. These do not cancel out. Remember, we are adding these. So that's negative 12. Just like in Algebra 1A on simple equations, if you get an always false statement, we will say this is an inconsistent system, which means it has no solution. So there's the answer, no solution. If they ask you to classify it, you would say the type is inconsistent. But the solution is no solution. You can write out the words, or you can write the empty set. The solution set is empty. Let's take a look at another example. Right, look at that second equation. They're all even. Let's make this easier. Let's cut it in half, just like we did before. So my second equation now is negative 3x minus 2y equals 6. My first equation is already in the standard form. So let me see if that makes it easier to do elimination or substitution. We're just going to add them up because we can already get rid of the x's. Hey, and the y's go away as well. This time we got a positive 6 added to negative 6, and that's 0. So when all the variables drop out, you have one of two things happening. Either no solution, that's when you get an always false statement, or infinite many solutions. So in this case right here, I show that I know how to do elimination, but if I stop right here, I'm not getting much credit, okay? I'd be lucky to get 2 out of 5 if I did this, or 4 out of 10. I need to state what my answer is going to be. So this is a dependent, if you want to state the type, it's a dependent system. Or you want to state how many answers, you can say infinite many answers. In Algebra 2 class, I'd probably give you maybe 3 out of 5 on this. College algebra, I'm expecting a little bit more to pass. I need to see that you're actually writing the answer. So there's 2 ways you can write it. If I would had divided this second equation by -2, I would have got the exact same equation as the first one. So I could use set builder notation like we did in Algebra 2. And say, hey, any point on this line is a solution. And that's what this notation is saying. It's saying any point right here, the xy, such that that point solves this equation. The other way to write this is the new way called the parametric way. We want to get good with this by the time we get to 2 assignments from now. So in parametric, what we want to do is we want to take that equation that we had, and we want to isolate one of the 2 variables, and it doesn't matter which one. So let me go get y by itself. So I would subtract the 3x, and then I would divide by 2. So what I'm saying is that the y would be what? 6 divided by 2 is 3. 3 divided by 2 is 3 halves. So the y coordinate is this formula, and it depends on the x value. And that's why this is called a dependent system. The y depends on what you plug in for x. So what I can do with a parametric equation, I could give you and find a formula to find out several points on there. So you just make a little table. So you can just go get a bunch of values. Like I could plug 0 in for x, and I get 3 for y. Or I could plug 2 in for x, even denominator, so pick even numbers. Okay, things that will be divided by 2. And let's see, the 2's would cancel out, and I'd get 3 minus 3, so 0. And I could give you as many ordered pairs as I wanted to. So this is telling you there's infinite many solutions, or any point that lies on this line, which both of these satisfy that original equation. All right. For our last example, we're going to do the classic college algebra linear system problem. We're going to do something with a current. Okay. So if you're going with the current, water's moving this way, and your boat is moving this way. So when you go with the current, you're actually going to go faster because you would add the rates. And if you go against the current, so if the water is going this way, but your boat is going this way, you would subtract the rates. And if you wanted the boat to actually move this way, opposite, the boat would have to be going faster than the current, or otherwise it would just float backwards really slowly. If you go the same speed, it doesn't move. So what you want to do is you want to do boat minus current. In this case, you want to do boat plus current. Now, sometimes people struggle with this, so I'm going to show you when we set up our table another way to do this. For these problems, I'm going to set up the common formula that goes with this. Distance equals rate times time. I'm just going to set up a little graphic organizer, a little table, to help me keep track of things. So in this problem, we have a boat traveling downstream. So we put downstream, 16 kilometers in 2 hours. That means you're going with the current. But if you don't have much experience going on a float trip or boating or flying in it with an airplane, the idea of downstream or with the current, sometimes it doesn't make sense. Think about walking on a moving sidewalks. When you go with it, you go faster. Okay, so we know we're going downstream. It says that it takes 2 hours to go 16 kilometers. Now you return or go upstream. So upstream is going against the current. You're going to go the same distance because it says you return the same distance. But this time it takes you longer. It takes you 3 hours. So if you're struggling with downstream and upstream, another way to think of it is if it takes less time, you have to be going faster. So when you start driving, you kind of figure that out. If you start speeding and going a little bit faster, it takes less time to get where you're going. Sometimes you don't want to go where you're supposed to be headed. Maybe you're going to work and you find out you're kind of going early, so you slow down and take a little more time. So if you take more time, you're going slower. So if I would do boat minus current, I'm going slower. So slower time goes with a slower speed goes with more time. If I go at a faster speed, a faster rate, it's going to take less time. So the smaller time goes with the add, the bigger time is going to go with the subtract. So these are my two equations. So I have, for my second equation, 16 equals 3b minus 3c. And my first equation, I could write it as 16 equals 2b plus 2c, but I could divide each side by 2 if I wanted to and make it 8 equals b minus c. That first one, everything was even, so I could divide it by 2 to make it easier. Put it in the true standard form. All right, so now I got to solve this system, and I could either use substitution or elimination. I'm going to go ahead and use elimination method here. So I'm going to take that first equation, and I'm just going to times it by 3. That was a plus there, sorry. And if I times it by 3, I get 24 equals 3b plus 3c. That would help me eliminate the c's. So now I have 40 equals 6b. Divide each side by 6. Both even, so only cut both numbers in half, so 20/3 is the same thing as 46. And now I use the correct labels. They said 16 kilometers, and the time was hours. So that's kilometers per hour for the speed of the boat. So if there was no current, that's the speed it would be going. If you want to do 6 2/3 or 6.6 repeating, any one of those three answers would be okay. 6.7, probably not going to accept for full credit. So there's the speed of the boat. Now we need to find the speed of the current. Well, go to an easy equation to work with, and I'll go to that first equation. I'll replace the speed of the boat with 20/3. And now I'm just going to go get this by c by itself. So let me convert that 8 into thirds. So times the top and bottom by 3. Subtract the 20/3. You may use your calculator at this point in time if you'd feel more comfortable. We're getting 4/3 or 1 1/3 or 1.3 repeating kilometers per hour. Make sure you clearly are stating which one's the boat, which one's the current. So if you're going to use x and y as your variables, you need to define x as boat and y as current. If you use the first letter, like B for boat, C for current, normally we can figure out what you're talking about pretty easily. So that's it for your notes. A lot of it, again, is review of what you've seen in Algebra 1, Algebra 2, to College Algebra A. You would have seen it there. Just watch out for those current problems. Those are probably the only thing that's a little bit different than what you've seen before. This is your assignment for this section. And then tomorrow we'll start up 4.2. Excuse me, we'll start up section 5.2.